In this video, we're briefly going to introduce spherical geometry. Now, spherical geometry, we're going to consider a plane, two-dimensional object in spherical geometry as the points on a Euclidean sphere, a three-dimensional Euclidean object. So specifically, let's consider a Euclidean sphere of radius 1. If we want to put a Euclidean coordinate system in, then we would put the origin at the origin of the sphere. And of course, then the equation for the sphere is rho equals 1. Of course, x squared plus y squared plus z squared equals 1 if we use a rectangular coordinate system. So we want to think of a line segment as a path of minimal distance between 2 points, as it is in Euclidean, taxicab, and hyperbolic geometry. Okay, and so it turns out, as we can see with our Leonard spheres, that if we just kind of stretch a string between 2 points tightly, it will adhere it to the surface of the sphere. It takes on an arc of a circle, specifically what's known as a great circle, or a circle which center is at the center of the sphere and the radius is the same as the sphere. Okay, so intuitively that's what we would mean by a line segment. In taxicab geometry, a line segment is the same as Euclidean line segment. It's one of many minimal paths between 2 points, paths of minimal length. But in hyperbolic geometry, Euclidean geometry, and spherical geometry, it makes sense to have there is a unique path of shortest length, and that will be our line segment. So, of course, we want to be able to take a line segment and extend it. That's the basic idea behind Euclid's first postulate, is that you can extend lines out. So we want to be able to extend line segments to longer line segments and eventually get all the way to a line. And so a line in spherical geometry then is just a Euclidean circle of the same radius and center as a sphere. So think of the equator of the Earth as an example of such a circle on the Earth, okay, or such a line if we think of the Earth as our sphere. This is sometimes called the great circle on the sphere. It also turns out to be both a Euclidean circle, and it also turns out to be a circle in spherical geometry as well as being a line in spherical geometry. So spherical geometry has this kind of unusual property that every line is also a circle, but of course not every circle is a line. So the maximum distance between 2 points is at most 1/2 the circumference of a sphere. So with the radius 1 sphere, this sets the maximum to be pi units. So this leads us to a bounded metric, as we discussed in some of the other tabs, other pages. So we have a bounded metric with least upper bound of pi. And it actually reaches that when we have 2 points which are exactly on opposite sides of the Earth, or opposite sides of the sphere. So for example, like the North Pole and the South Pole on Earth. Those are called antipodal or polar opposite points. Okay, and notice that such points exist. There exists a maximum, points which are at a maximum distance do exist in this geometry. There is no such thing in Euclidean, taxicab, or hyperbolic geometry. There are no 2 points which are as far apart as you can make them. No matter how far apart you put 2 points, in those geometries you can go one farther, a little bit farther. Whereas, so it's unbounded. But in spherical geometry, 2 points can be a maximum distance apart, and that maximum distance is pi with the setup that we're using here. So with our usual definition of a ray as half a line, it's a great semicircle. So let's think about this a minute. If we look at the line AB, certainly it's going to include the line segment AB, which would be this arc right here. So let's take this right here and consider this. Construct a arc through 3 points, and so this would be an example of a line in a sphere. So this is going around the sphere. Okay, and of course any points in, so all of this is part of the line. Well, remember a ray, it's also part of a ray. So the ray is the points A and B, the line segment AB, and any points D such that B is between A and D. So notice here B is still between A and D, and that goes up to and includes this antipodal point A prime, which is on the opposite side of the sphere from A. So there's a ray. if we continue on like this, this is neither a line segment nor a ray, because now points B and C here are not between D and A. Points in between D and A are on the dotted part up here. So this is not a ray. A ray will be half of a line, and that makes sense here once again, like it does in Euclidean sense as well. Half of a line. So a ray has a finite length of pi, and a full line has a finite length of 2 pi. Okay, because of the circular nature of the lines in spherical geometry and the resulting bounded metric, we have to be kind of careful about some of the postulates and propositions if we want a unified treatment for all 4 of these geometries. So we have to modify a few to be accurate in spherical geometry. Everything that we've talked about thus far in the course, the postulates and propositions, everything work equally well in Euclidean, taxicab, and hyperbolic geometry. But just a couple of them have to be modified a bit, or they just don't really apply in spherical geometry. So for example, in Euclidean geometry, if B is between A and C is between B and D, then we can get the order A, B, C, D. Well, that makes sense for as long as this length, the distance between A and B, is less than pi. But, well, I mean, the distance is always pi or less. But if the shortest path to A to D is along the other side, like this, and we put B here, for example, we still have B is between A and C is between B and D, but we cannot really say A dash B dash C dash D, because B is not between A and D, and C is not between A and D. In fact, yeah, so we have some different relationships that you have to be careful of. Okay, so we can, however, put a coordinate system on a line, and a coordinate system on a line in spherical coordinates would look like this. So we pick an origin here, and we can go around here. This is 1, 2, 3, up to pi. Going this way, we have negative 1, -2, -3, up to but not including negative pi. So the coordinates go from negative pi to pi, not including negative pi, but they do include pi. And so now we can have a point P here, which we can move around, and you see that that it's showing the coordinates of P. And notice they go from almost negative pi up to and including somewhere in here. It actually hits pi. Okay, and so you can see that. Okay, so that's an update to the sketch for this week, and I'll repost this. And we got one more video of the basic lectures for this week that I'll get to a little bit later, and that will be going over some of the formal propositions about distance and order. And we've gone over some of this in an earlier system already, but we'll go over we'll kind of run through some of this material, at least in what it's saying here in the next video.